Welcome everyone. In this episode, we are going to cover chapter 2 of the book Deep Learning with Pytorch. I'm doing this to promote diversity in tech, and I'm super happy you are following along. I want to start by showing you the Fast AI forum page in which I'm telling about these episodes, as well as letting you know that I have created a playlist on YouTube to keep this content a bit more organized as I see the number of videos increasing. So, what are we going to do today? I'm going to talk a bit more before just jumping straight into the book about the setup because once I was reading these chapters, I realized of a couple important things that maybe I had left out. So, as I told you, I'm using SageMaker, which is kind of Jupyter notebooks on AWS. Then I was using this notebook in here, Pytorch book. And I realized that actually the book, let me look for it. Yes. So that's our book, right? From Manning. And it has two repos. And the second one is what I'm going to be using today. And I haven't been, well, I mean, we are going to use both of them, right? But the second one I had not added to our code, right? So I'm going to be doing it now and I want to show you how to do that. And I also want to show you one thing that's important, which is um, that you have to remember to stop those notebooks because otherwise you're going to be charged. I told you like SageMaker notebooks is just the manage EC2 instance, right? So if you don't turn off, if you don't stop that EC2 instance, you are being charged for the time it runs, which in the case of that one I'm having here, it's about like $3 an hour. Good. So how do you do that? So I mean now it's already stopped. You see it in status. So I'm gonna be able to update settings. And if you remember, that's what we configured it at the first day. And here I have my Git repos. And what I'm gonna do is I'm gonna add an additional one, and it's gonna be again a public one. And I'm just gonna put it the address in here, and I'm gonna do update notebook instance. And now I can start my notebook instance. And at the beginning, you will think maybe nothing happens, but then it just takes a while. And sometimes if you get these UR errors, it's probably because you click too fast at the bottom 2 times. A bit of annoying. Okay, so I'm gonna now it's pending, and while this is pending, I'm gonna jump straight to the chapter and then come back to it. Okay. So I have my chapter open here. So chapter 2 is all about fun, and the topic is pre-trained networks. So this chapter covers running pre-trained image recognition models, an introduction to GANs and CycleGAN, captioning models that can produce text, description of images, and sharing models through Torch app. So let's now jump into the text. We closed our first chapter promising to unveil amazing things. And now it's time to deliver. Computer vision is certainly one of the fields that have been most impacted of by the advent of deep learning for a variety of reasons. The need to classify or interpret the content of natural images existed, very large datasets become available, and new constructs such as convolutional layers were invented and could be run quickly on GPUs with unprecedented accuracy. All of these factors combined with the internet giants' desires to understand pictures taken by millions of users with their mobile devices and managed on said giants' platforms, they were quite the perfect storm. So I think the authors are trying to say many factors came together and it was just like the perfect time, right? So what we are going to learn how to use the work of the best researchers in the field by downloading and running very interesting models that have already been pre-trained on open large-scale datasets. We can think of a pre-trained neural network as similar to a program that takes inputs and generate outputs. And I think that's very important because in this chapter we are not going to be training models. We are just going to leverage the job of others by using pre-trained models. And that's why we can do it with a very light hardware actually, right? If you were doing with a T2 medium, you would perfectly be able to run it. So it says in the chapter, we will explore three popular p-train models. One, a model that can label an image according to its content. Two, a model that can fabricate a new image from a real image. And three, a model that can describe the content of an image using proper English sentences. And we will learn how to load and run these pre-trained models in Pytorch, and we will introduce Torch App, a set of tools through which Pytorch models, like the pre-trained ones we will discuss can be easily made available through a uniform interface. Awesome. So what they're also telling you is that, if you're coming from Pytorch, from another deep learning framework, such as like TensorFlow, you just might as well skip this chapter. But that being said, they hope you don't, because they will teach you some important skills under the fun. And I honestly think this chapter has been really lots of fun. Okay, so the first one we're going to look at is this pre-trained network that's able to do object recognition. And they are telling you that we're going to use a data set called ImageNet. And that's a very large data set that covers over 40 million images, and it's maintained by Stanford University. And it says the ImageNet dataset, like several other public datasets, has its origin in an academic competition. And this competition is among others, the ImageNet Large-Scale Visualization Recognition Challenge, which has gained popularity since its inception in 2010. And they tell you, this competition was based in a few tasks, and they could vary each year, but there was like image classification, which is telling which category an object is, image localization, which is like identifying the position of an object in an image detection, which is both things, a scene classification, which is like describing a situation in a scene, and so on and so on, right? And we are going to be focusing here in classification. And they tell you it's a huge amount of images, like 1.2 million images labeled. And labeled how? Well, they're going to get like 1 out of 1,000 categories. And these categories is what we call label or class, right? And we will use the word label or class interchangeably. And that's important because sometimes, computer science class has another meaning, like in object oriented programming, what's a class, right? So here they show you a bit of how those images look like. If you know a bit the data set, you will see that there are lots of cats and dogs. So if you have seen things like Deep Dream, you know that cats and dogs appear like a lot. If not, it's fine. Just saying some extra stuff. And look, that's what we're gonna do, right? We are gonna take an image of a dog, Bobby, and we're gonna prepare this image. We are gonna do some resizing. We're gonna center crop that image. We are normalize the intensities of the image, and we're gonna pass it to our convolutional neural network. And for now, we are gonna treat that just as a piece of software. Some black magic has been going on inside, has been trained, but for us, it's in and out. And what's the out? Well, it's basically some probabilities. So they all add to one, right? And there are 1,000 classes because we said there are 1,000 different types of pictures. And then, we will look at the top one or at the top five of those labels, right? And I think that's the most important takeaway. And maybe to start introducing some of the book terminology, they talk for the first time of the concept of tensor. And they say, tensor in physics and they can have like very scary meanings. But for us, a tensor is just like a multidimensional array. Like you would call anything that's over like a 3D array, you would say that's a tensor. And I think that's very important. Yeah, so they are telling you um, we have this pre-trained network, and we have in Pytorch something called, maybe I should mark that, the Torch Vision project. And basically, they were creating a common interface to use all those vision models, right? And Torch Hub is a much broader project, a much broader option, right? But we're talking now here of Torch Vision, and what they're going to be showing us in code is how to import those models out of Torch Vision. And those models that we will be seeing, and there are many of those models, right? Many of those convolutional neural networks that have been pre-trained for you. But here in this book, they talk about AlexNet, which was the winner in 2012. Let's mark that maybe also too. And they say it was the winner by a very large margin, right? So they achieved an error of 15%, while the one that came next was 26. So it was a huge gap, right? And that showed the potential deep learning had for the first time. yeah, and I think it's also relevant to know that nowadays we're getting like top 5 error rates as low as 3%, which is actually better than what a human can do, right? Which is fantastic. And that's AlexNet. Look, it's just a bunch of filters, right? So generally, what happens in many of these convolutional neural networks is you are getting more filters, more depth as you go through the network until you flatten out. And if that makes sense to you, fantastic. And at the same time, you're squishing your image and making it smaller, right? And usually you are able to understand very well what happens at the first layers and what happens at the very last. But here you have little visibility or little understanding. And if that made sense to you, it's fantastic. If not, it's also not very relevant, because all you need to know for this chapter is that we will be using this model and a bigger one, which is called ResNet. And the difference is the amount of layers these have, right? So as you can see, this is a rather small network, while ResNet, for instance, 101 has 101 neural convolutional layers, which at that time in 2015, when it won the competition, it was an incredible achievement. And they managed to do that thanks to the concept of skip connections, right? So I'm just saying we are going to be playing here in with two models that really set a new standard in the field, and I think that's super great. Okay, so let's do that. I'm gonna go back to my AWS account. I'm gonna open in Jupyter Lab. Awesome. And you see now we have both of my repos, the one I cloned a couple days ago and the last one. And I'm gonna go to part one, chapter two, and I'm gonna go pre-trained networks. And I already ran yesterday this code, so I can be today a bit faster and show you the outputs. So first from Torch Vision, this vision project, we are going to import models. And if we do their models, we see all those models that we have in there, right? So you see the fact that the book says start with a capital letter means they are classes. And what we do next is we are we are calling one of those classes, right? We are instantiating here AlexNet. And we are also doing the same for ResNet. And notice that we are doing pre-train true. And then when we do that, something downloads. And and if you ask yourself, what is this download? Well, that's actually all those weights, all those parameters. If you imagine your convolutional neural network like many linear and nonlinear functions, then you need those parameters, and that's those weights is what we are downloading here, right? And then we can visualize ResNet, and you see here these blocks that are being repeated, and you will see that they always include these conf layers, batch norm, relus, and so on, this sequence. Yeah, so I'm gonna like scroll down because that's very long. Good. And what we're going to be doing next is think how we want to prepare the image. And we are going to use, and due to that, we are going to transform our image. So that's why we are importing transforms. And we are going to do compose because we are using several of them, right? And we are going to resize our input image, which is going to be Bobby. That's Bobby. We're going to resize it to 256. Then we'll do a center crop. Then we will convert it into a tensor because by default will be like an NumPy array, not a tensor. And then we will normalize it. And those are the mean and the standard deviation of the ImageNet stats. And you see three values because color images have three channels, RGB, right? Red, green, and blue. So yeah, that's basically it, right? We take an image and we do some processing. Wait, where are we doing this processing? We are doing this processing here, right? So that's the pre-process. And now our image is a tensor. But it's just a single images. And usually these networks will expect to get batches, so like collections of images. So that line might confuse you a bit because we are unsqueezing to get out of an image one batch of a single image. And then we are putting our ResNet, our network, in evaluation mode because if you have things like dropout, you know that for evaluation you want to turn it off. And that's what we're doing here. Um, if that doesn't make sense, just the takeaway is you have two modes, train and eval, and when you're doing inference, you want to have it in eval. So skipping all that, good. So now what we are doing is we are taking our batch with one single images and we are passing it through the network and we are getting out a tensor that is huge because we have how many? 1,000 classes. So we need a better way of interpreting that. And luckily we have a file that contains the labels, right? So we're gonna be reading each of these and save it in a variable called labels. And what we will do next is out of this tensor with 1,000 classes, we're gonna take the maximum value, right? So if you realize they are all basically super close to zero, except one, which is hopefully very close to one, and that's our right class. And we are passing, so we're taking the output, we are passing it to a softmax to get this range. So basically, to get exactly what I was saying, right? To get the values between to add to one, and one will be very big. And instead of getting 0 0.9 or 0.99, we will be multiplying by 100. And then we will be passing that into our labels because what we are going to be getting here is not only the percentage, but also the index, the position. And we are going to use that index to retrieve the right label. So what we are going to getting is golden retriever with 96% probability. But we can do even one thing more, which is like we can now, instead of take the max, do sort with descending true. So and we can take 5. And that's what ImageNet requested, right? The top 5 or top 1, top 5 error. So the golden retriever is still the same one. And then the other 4 are still dogs, which I think it's very reassuring. And I think it's fun to see how the last one is a tennis ball, because I think it's easy to guess what happened, right? That the network probably has seen dogs holding a tennis ball, and the network is telling you maybe I have misunderstood what a dog is since there were so many tennis balls when I saw dogs. Yes, so I think that was a very very fun example, and I think it's also a nice notebook to play with your own images, and if they are part of the ImageNet categories, you probably get good labels. Now, what comes next? So we have covered all that. We were very fast. Okay, the next one is a pre-trained model that fakes it until it makes it. And that's the GAN game. And for the GAN game, I want to recommend you actually a video on YouTube from Computer File, and that's a very very good YouTube channel. And I find it especially good when the one who explains is Rob Miles, right? So I probably should be pointing you towards this other video from Ian Goodfellow in the podcast of Lex Friedman, which is also very good. Uh, so probably honestly check both, but this one was such a great interview. I totally recommend it because probably otherwise you would check this out, but not this one. Yeah, so okay, sorry. Then look at his video for a very nice explanation. I'm gonna give a super nice, a super short explanation of GANs. So first I'm gonna read this paragraph. In the context of deep learning, what we have just described is known as the GAN game, where two networks, one acting as the painter and the other one acting as the art historian, compete to outsmart each other at creating and detecting forgeries. GAN stands for Generative Adversarial Network, where generative means something it's being created, in this case, fake masterpieces. Adversarial means that the two networks are competing, and well, networks is pretty obvious. So look, let's look at this picture, and I can explain way better with that picture, right? So first, the goal. We are trying to convert the picture of a zebra into, the picture of a horse into a zebra. But you will also see GANs used a lot, for instance, um, to create stuff, to create people that don't exist. There is this famous page. Let me see if I can find it. This person does not exist. And those are also fake pictures of people who actually don't exist, right? Even though they look super real. And that was also done by GANs. So GANs are okay. This one definitely doesn't look that nice. GANs are simply amazing. Yeah. Yeah. Sorry. Coming back to the topic. So that's a probably a super cool example. What we're gonna do here is converting horses into zebras. And it's a model that uses two different components, a generator and a discriminator. And let's say, imagine the generator as someone who's trying to fake a Van Gogh or a Picasso. And the discriminator is, the art critic that knows the differences. And of course, it would be very difficult for you to fool the critic at first, right? But if the critic is telling you, I'm not buying your stuff because that's bad, then you will use that information to fix it. And what I'm getting at is those are two competing networks, two adversarial networks that are using the feedback of one another to, so to say, improve, to, in deep learning words, train themselves, right? So we start with random noise, then we pass through the generator and we get something which is super weird. And then, the discriminator is able to say real, fake, and he wins, right? And with that information, we are going to adjust our network, right? And maybe we fool the generator. And then with that information, we will adjust the discriminator. And that's what they call the GAN game. And then there is even an interesting evolution of this concept, which is the CycleGAN. And the CycleGAN can turn images of one domain into the images of another domain and back, without the need of us explicitly providing matching pairs in the dataset, right? So in this figure below, what we have is the task for turning a photo of a horse into a zebra and vice versa. But note that we have here two separate generators and discriminators, right? And they said it's something that it was used actually as a trick to stabilize GANs, which was one of the biggest problems of GANs. And they tell you, it's enough of like providing some pictures of horses and some pictures of zebras. You don't need to have pairs. Like the model will learn, so to say, the distribution of what a horse looks like and what a zebra looks like. And I think that's also super cool. So I think that's basically all I wanted to say. What we're going to do is now use this model, the ResNet generator. Uh, so to do that, let me again go back to the code. Not this tab, this tab. I think here, yeah. So CycleGAN. So I think way more long, but actually they say, we are not gonna go into the detail of all these. We just want you to understand the main concept, right? So what I want you to take out of it is they are importing Torch and the neural network module so that they can define these classes. They can define what a ResNet block is and the ResNet generator, right? And what they do next is, now that they have defined the class, um, meaning class here, the object-oriented class, not the label thing, they will instantiate it, right? And then what they will do next is they will load the model data, right? So those are the weights, because if you had to train that, it would take you very long. But here, with that model that now is just basically full of noise, and those weights, we can load them and basically get a message back that all we have managed to load all the parameters successfully. If, for instance, your architecture was different, you would get here an error, and that's important. Then again, we put it into evaluation mode. And then with the pillow image from Python, we import and open an image of like a guy in a rodeo. And again, as before, we are going to transform the image. We're going to resize it. We're going to pass it to a tensor. we're going to make it, we're going to pre-process it, we're going to make it in a batch, we're going to pass it through the network, and then we're going to get the output out of it, which we have to, if before we had unsqueeze, now we had to squeeze, and then we had to add some scaling values, and then we have to transform back, and boom, that's our guess zebra cowboy. And what they say in the exercises, so I'm skipping here one step, is why don't you try with Bobby? So what I'm doing is I'm now fitting Bobby, I'm pre-processing it in the same way, and that's what I'm getting out of the network, which is doing, I guess, its best at trying to make a zebra out of a dog. Yeah, so I think that's basically it. So let's jump now to the third and last example, which I haven't tried yet. So let's see how that goes. It says a pre-trained network that describes scenes. In order to get first-hand experience with a model involving natural language, we will use a pre-trained image captioning model generously provided by Root 1 Law. It's an implementation of Neural Talk 2 by Andrew Karpathy. When presented with a neural image, this kind of model generates a caption in English that describes the scene. So let's see a bit more in detail. Basically, we have an image, and then the model has, I think, two parts. One is like a convolutional neural network that probably will say a guy or balloon. And then we have a recurrent neural network that would take its words and try to come up with a sentence that makes sense. An odd-looking fellow holding a pink balloon. Okay. And it says this captioning model has two connected halves. The first half of the model is a network that learns to generate descriptive numerical representation of the scene, tabby cat, laser pause, pow, which are then taken as an input of the second half. And the second half is a recurrent neural network that generates a coherent sentence by putting those numerical descriptions together. So the two halves of the model are trained together on image captioning pairs. Okay, and I think that's maybe also important to say. The second half of the model is called recurrent because it generates its outputs individual words in subsequent forward passes, where the input to each forward pass includes the output of the previous pass. This generates a dependency of the next word on the words that were generated earlier, as would be expected when dealing with sentences in general with sequences. Okay, I think that was a bit dense, right? But I think the main idea is clear that we are going to pass an image, some black magic happens here, we get a caption back. And this black magic is actually two different networks. And with one we are already familiar because ImageNet was basically like the ConfNet that we were looking at before was just for ImageNet was the same, right? We were getting an image and we were getting a label. Just that here, this label is gonna have it's gonna be part of a nice sentence thanks to this recurrent neural network. And what I did is there is this super nice video from Andrew Karpathy, who now which in the book was mentioned, right? And who now is like the senior director of artificial intelligence at Tesla. And he explains all these recurrent neural networks super nicely. So I would recommend you to definitely check out his video. I think he has some very nice explanations, and I think what I wanted to show you here is just with like the word hello, but you can imagine it in our model with different words as how the first word you get as an input, then you will generate the immediate next word in the sequence with it will be your input and so on until you create the whole sentence. Yeah. Um, I think it's a pretty interesting topic. I also want to mention that the authors say they will not talk anymore about recurrent neural networks in the book. You will see more of convolutional neural networks, but if you are into natural language processing, then that's probably something you want to look elsewhere. Yeah. So let's see how they say that we have to run this network. Okay, so it says okay, that the neural 2 talk can be found in this GitHub repo, which I have cloned. And then we can place a set of images in the data directory and run the following script. Okay, so I guess I have to copy this. Let's see if that works. And let's see. I have my data. Ah, nice. So how can I do that? Maybe let me pause in here, figure it out, and then I'll start again. Okay, so it's actually a bit embarrassing because I couldn't figure it out what's wrong. But I'm gonna show you what I tried because I think I'm pretty close. It's getting late in Central European time. Um, so maybe you can correct it and tell me in the comments. So okay, basically I chose an image of a dog playing with a ball. And what the author tells you is, you have to basically, that's the other repo we clone, and you have to go to this one and make sure you put your images in this data folder, right? And here I put my dog image both as a JPEG and a PNG. Didn't seem to help, but kind of that's what I tried. And then what I did next was I opened a terminal. Then in SageMaker, one thing that you have to be careful is that by default you are in the root folder. So you want to go to SageMaker, and here you will find the two repos, and then you want to go to the correct one, right? And here you have this eval.py file, and the command they'll tell you to run the script is, wait, let me copy it right. So in the book it tells you you should run this line and the next one. So that's what I'm gonna try to do. And I will get an error, but that's normal and I'll tell you why. So I'm copying this one and then this other one, right? And I think that to me makes perfect sense. So basically you're doing Python, run the eval.py file, which is now here, like me, so that's fine. And my model is in here, and my info path is in here, and my image folder is data, in which I place my pictures, which is what the book says. So yeah, that's pretty much it. Now I could run this line, and probably gonna do it and stop, but I'm gonna get immediately an error, which is no model name torch, and that's because I'm in the base environment, right? So I'm not in my kernel. So if I do conda um, conda list, I'm gonna get all the list of kernels. I'm gonna do source activate Pytorch p36. Good. And now I can run again this line, and I should, according to the book, be able to get here my caption. But instead, I'm getting this weird error, as if no images were found in this directory. And I look at it like 10 minutes. Honestly, guys, I don't get it. So if somebody knows, just please let me know in the comments. What I'm going to do now is just skip that part and explain Torch Hub, which is the last section of this chapter, and says pre-trained models have been published since the early days of deep learning, but until Pytorch 1.0, there was no way to ensure that users would have a uniform interface. And then Torch Vision was a good example of how to solve that for, vision models. But authors that had seen CycleGANs or Neural Talk 2, they chose different designs. So basically, Torch Hub was a mechanism so that authors can publish models on GitHub with or without pre-trained ways and expose it through an interface that Pytorch understands. This makes loading a pre-trained model from a third party as easy as loading a Torch Vision model. And now it's very interesting because they show you how to actually load these Torch Vision models as if they were just like one of these generic other models in that you will load with the Torch Hub interface. And they'll tell you to do that, they follow a very simple structure. You just need to define some entry points, and you need to have this file, the hubconf.py file. So that's really the only thing you need to know. And then you can just, before we are doing from Torch Vision import models, and now what we are going to do is from Torch import hub, and then hub.load, and then you have the name of your repo, the branch, which is master, then the entry point. So for instance, in this case, the entry point is ResNet 18, and then you're going to say pretrained equals true because you want to download the ways. Otherwise, you would say false. So that's basically all there is to it. So that means that if I go to, I'm going to do that. I'm going to go to GitHub Pytorch slash Pigeon. Let's see if it checks. I'm going to go and do GitHub um, Torch Pigeon. And they told me I should found this file in here. And in this file, I should find my models. Yes, nice. So, and maybe if I even go, could I find Torch Pigeon? Maybe I'm getting into a mess in here. Models. And I want to look for, let's say, one of the ResNets. And those are the weights that I will be downloading. Ah, and those are the building blocks. Oh, sorry. I know I'm getting excited myself. But yeah, I think that's what I wanted to get. You see, here you have the model and here you have the true or false, and we also have found the conf.py file in here. In Once more in here. So yeah, basically it checks. So that's it. I'm gonna read now the summary of this chapter. So let's say conclusion. We hope this chapter was fun. Yes, it was. We took some time, a lot, to play with models we created with Pytorch that were optimized for several tasks. Um, but we will also see how building models that deal with different problems on different kinds of data can be done using the same building blocks. And one thing that Pytorch does particularly right is providing those building blocks in the form of an essential toolset. And it says Pytorch is not a very large library from an API perspective, especially when compared to other deep learning frameworks, just TensorFlow. This book does not focus on going through the complex Pytorch API, but it gives you, hands-on knowledge. Yes, we practice a lot and building blocks to, acquire solid foundation, blah, blah. Summary. A pre-trained network is a model that has already been trained on a dataset, yes. Such networks can be typically produce some useful results immediately after loading the network parameters. By knowing how to use pre-trained models, we can integrate a neural network into a project without having to design or train it, yes. So if you're a software developer, that's super useful. AlexNet and ResNet are two deep relatively networks that has set new benchmarks for image recognition in the years that were released, yes, 2012, 2015. GANs have two parts, the generator and the discriminator. They work together to produce output indistinguishable from authentic items. Yes, we talk about forgeries. CycleGAN uses an architecture that supports converting back and forth between two different classes of images, zebras and horses in our case. Neural Talk 2, which we failed, uses a hybrid model architecture to consume an image and produces a text description of the image. And finally, TalkHub is a standardized way to load models and weights from any project with an appropriate hubconf PI file. Woo, that was intense. So that was it for today. Chapter 3, we are going to be looking into tensors. It all starts with a tensor. Thanks for watching.